In blocking send and blocking receive, both senders and receiver are actually blocked until the message is delivered. Actually, sometimes we refer to this situation as rendezvous. Using this strategy of blocking both the senders and the receiver allows for tight synchronization between processes. So on the other hand, we could support non-blocking send and blocking receive. Although the sender may continue on, the receiver is blocked until the requested message arrives. This is probably the most useful combination. It allows a process to send one or more messages to a variety of destinations as quickly as possible. A process must receive a message before it can do useful work would need to be blocked until such a message arrives. An example to this is a service process that exists to provide a service or resource to other processes. If we are talking about the freedom of non-blocking send and non-blocking receive, that means neither party is required to wait. So another design issue that arises in message passing mechanism is related to addressing. So clearly it is necessarily to have a way of specifying the send primitive. In the send primitive, which process is to receive the message. Similarly, most implementations allowing a receiving process to indicate the source of a message has received. The various schemes for specifying processes in the send and receive primitive fall into two categories, either direct addressing or indirect addressing. For direct addressing, the send primitive include a specific identifier of the destination process. The receiver primitive can be handled in one of the two ways. One possibility is to require that the process explicitly destinate a sending process. Thus, the process must know ahead of time from which process a message is expected. This will often be effective for cooperating concurrent processes. However, in the other case, it is possible to specify the anticipated source process. An example is, we can see it like in a printer server as an example. A printer server process which will accept a print request message from any other process. And as a matter of fact, for such applications, a more effective approach is the use of implicit addressing. So implicit addressing at this point, the source parameter of the receive primitive will actually possesses a value returned when the receive operation has been performed. So this is the implicit addressing. On the other hand, the other general approach is indirect addressing. In this case, messages are not sent directly from sender to receiver, but rather are sent to a shared data structure consisting of queues that can temporarily hold the messages. Such queues are generally referred to it as mailboxes. At this point, for two processes to communicate, one process sends the message to the appropriate mailbox, and the other process picks the message from the mailbox. A strength of using indirect addressing is that by decoupling the sender and the receiver, well, this decoupling will allow greater flexibility in the use of messages. So the relationship between the sender and receiver can be either one-to-one or one-to-many, many-to-one, or could be one-to-many or even many-to-many. In a one-to-one relationship, it allows a private communication link to be set between two processes. This insulates their interaction from any interference from other processes. On the other hand, the many-to-one relationship is useful, especially for client and server interaction. One process provides service to a number of other processes. In this case, the mailbox will even refer to as board. A one-to-many relationship allows for one sender and multiple servers, multiple receivers. It is useful for applications when a message or some information is to be broadcasted to a set of processes. Finally, a many-to-many relationship allows multiple server processes to provide concurrent service to multiple clients. So for the one-to-one relationship, to summarize, it allows private communication link to be set between two processes. It insulates the interaction between processes from any interference of other processes. For the many-to-one relationship, it's useful for client and server interactions. And then the mailbox will be called board. Keep this word in mind. This now we use different terminology for the mailbox. On the one-to-many relationship, it is used for application where there are some information to be broadcast to a set of processes. Finally, for the many-to-many relationship, it allows multiple server processes to provide concurrent services to multiple clients. Keep in mind, the association of processes to mailboxes can either be static or dynamic. Ports are often statically associated with a particular process. That means the port is created and assigned to the process permanently. Similarly, for one-to-one relationship, it is typically defined statically and permanently. When there are many senders, the association of a sender to a mailbox may occur dynamically. Primitives such as connect and disconnect may be used for this purpose. Um, The format of the message that will be sent between sender and receivers depends on the objectives of the message facility, as well as whether the facility runs on a single computer or in a distributed system. For some operating systems, designers have preferred short, fixed length messages, and the reason for this is to minimize processing and storage overhead. If a large amount of data is to be passed, the data can be placed in a file, and the message then simply reference that file. A more flexible approach is to allow variable length messages. In this figure, we can see a typical message format for operating systems that support variable length messages. The message is divided into two parts, a header and a body. The header may contain information about identification of the source, the intended destination of the message, the length field, and a type field to discriminate among various types of messages. We can also have additional control information, for example, like pointer field. If we are talking about linked list of messages that might be created, we might need to have a pointer field as a control information. We might even have a sequence number that can be used to keep track of the order of messages that are passed between the source and destination. We can even have a priority field if we would like to identify priority for messages. And then a body, which actually contain the actual content of a message. Finally, another design issue comes with the implementation of message passing mechanism to enforce mutual execution is the queuing discipline. The simplest queuing discipline, as we learned before, is the first come, first serve, or first in, first out. But this may not be sufficient if some messages are more urgent than others. An alternative is to allow specifying a message priority on the basis of message type or even by destination. This could be done by the designation of the sender. Another alternative is to allow the receiver to inspect the message queue and even select which message to receive next. So in the following figure, we can see one way in which message passing can be used to enforce mutual exclusion. We assume the use of blocking receive primitive and non-blocking send primitive. So we do have here blocked receive and non-blocked send. So a set of concurrent processes will share a mailbox that's called box, and which can be used by all processes for either sending or received. So this is we were initially creating the box, and the box is initialized to contain a single message with null content. So you can see it is initialized by just like one single message with null content. It has nothing. This is in the create mailbox function. A process wishing to enter its critical section, it will first attempt to receive a message. If the mailbox is empty, then the process is blocked. Once a process has acquired the message, it performs its critical section and then places the message back into the mailbox. Thus, the message function, we consider this as a token that is passed from a process to a process. This solution assumes that if more than one process performs the receive operation concurrently, then if there is a message, it is delivered to only one process and the others are blocked. Or if the message queue is empty, all processes are blocked. When a message is available, only one blocked process is activated. And given the message, the process will, once the process receive a signal, or like a send operation, then the process will be out of the mailbox. Will receive a message from the mailbox. These assumptions are true of virtually all message passing facilities. Like it could be applied to any message passing facility that would like to enforce mutual execution. Again, this example shows how the message passing can be used as a solution to the bounded buffer producer problem. If we're going to use the basic mutual execution power of message passing, the problem could actually have been solved with an algorithmic structure similar to what we can see in this figure. So in this figure, we take the advantages of the ability of message passing to be used to pass data in addition to signals. We do have two mailboxes that are used at the producer. So we do have the may produce mailbox and we have the may consume mailbox. As the producer generates data, it is sent as messages to the mailbox may consume. As long as there is at least one message in that mailbox, then the consumer can consume it. Hence, the may consume would serve as the buffer. And the data in the buffer are organized as a queue of messages. And the size of the buffer is determined by the global variable capacity. Initially, the mailbox may produced is filled with a number of null messages equal to the capacity of the buffer. The number of messages in the may produce mailbox shrinks with each production and grows with each consumption. This approach is quite flexible. There may be multiple producers and consumers. As long as all have access to both mailboxes, the system may even be distributed, with all the producer processes and the may produce mailbox at one side, and all the consumer processes and the may consume mailbox at the other side. So an exercise for you is to go over the reader and writer problem, which is similar to the producer and consumer problem, in which there is a data area that are shared among a number of processes. And the data area could be of any shape. It could be file, or could be block of memory, or could be even a blank processor registers. And the condition that must be satisfied to enforce mutual execution, that a number of readers may simultaneously read the file. Only one writer at a time may write to the file. And if the writer is writing the file, no reader may read it. So the readers are processes that are not required to exclude one another. And writers are processes that are required to exclude all other processes, readers and writers alike. So you could review the following solution using semaphores. Using the semaphores that show how we could actually enforce The semaphores, the mutual execution using semaphores to solve the reader and writer problem. And at this point, the writer process is simple. The semaphores, which is called WSIM, is used to enforce mutual execution. As long as one writer is accessing the shared data area, no other writers and no readers may access this data. The reader process also make use of the semaphore to enforce mutual execution. However, to allow multiple readers, we require that when there is no readers reading the data from the buffer or the file from the file, the first reader that attempts to read should wait on the semaphore. When there is already at least one reader reading, subsequent readers need not wait before entering. And also the global variable read count is used to keep track of the number of readers, and the semaphore acts, say like it's here, so we have another semaphore X over here, is used to ensure that the read count is updated correctly. So you just need to go and review these solutions to provide a way of solving the reader-writer problem. Similarly, we did in the semaphores. And if you go over different codes, you will see how this was implemented using either semaphore, and as a matter of fact, using an example over here is using message passing. So that's like a kind of homework for you to see how message passing and semaphores can actually be used to provide solution for the reader and writer, similar to what we did in the producer and consumer example. So a summarization for this lecture is so far we talked this lecture and last week we talked about Dekkers and Peterson algorithms. We started introducing the principle of concurrency. In today's class, we focused on the mutual execution using hardware support. We start talking about semaphores, monitors, and message passing. And then an exercise for you is to review the code to provide solutions for the reader and writer problems using semaphores and monitors even, and using message passing. So this is the end of today's lecture, and thank you for listening.